Okay guys, welcome back. From this video onwards, I will shift to my own version of Mathematica installed on my computer. You can continue to work on the web version of Mathematica on the Wolfram Cloud, or you can use a natively installed version on your desktop. In today's video, we'll talk about visual thinking. Visual thinking is about learning how to represent the information, data, or our understanding or knowledge in form of a picture or a graph or a plot. It is also useful in solving problems. We'll also learn how to take some piece of the problem and apply visual thinking to it, so that we can represent piece of the problem in form of a graph, so that our understanding about the concept of the problem can improve. And finally, the third use of visual thinking is to interpret the data and improve our understanding of the problem. The final results, we represent the final results in terms of a graph or a plot, and then we use that to understand and infer from that. Okay, so let's get started with today's lecture. So what is visual thinking? Visual thinking is ability to represent and interpret data or any other information through a visual medium, such as data chart, a graph, a picture, a mind map, a relationship map, flow charts, etc. So visual thinking can be any of these many things. Visual thinking is also a way to organize your thoughts and ability and think and communicate. Remember that picture is 1,000 words. A picture can say a lot more than what you can write in form of text or even express through equations. In this course, we'll learn visual thinking throughout the course and how to do visual thinking on a computer, how to take the information that we have in our problems and how to represent it on a computer. So visual thinking is a very wide word. It can mean many things. It can also mean representing your thoughts and ideas through an abstract painting, but that's not what we are referring to. We are referring to visual thinking as where we take physics and maths problems and represent them on a computer through visual media. Let's move ahead and get started with something. So we'll learn how to plot a graph. I've already given you some introduction, so I'll move through this really fast. Let's start out by a very simple function, such as a linear function. The linear function in question here is 2x minus 5. I want to plot 2x minus 5, and as discussed last time, you can simply use the plot command. Express the range of the variable. The variable is x over here, and the range is x from minus 5 to 5, and you can say a plot style, and then you can go ahead and execute the command. When you execute it, and this is the output you get. What I can do is I can actually make this thicker, maybe by adjusting the thickness. So these little tricks we'll keep on learning as we go along in the course. So this was simply plotting a linear function. Let's go ahead and make our life a little bit more complex and plot a polynomial. So here's an example of polynomial: x cubed minus 4x squared plus 1. When I execute it, I get this plot. Let's change this. Let's make it 3x cubed. Or maybe we can increase this, make it 12. Now you see, whenever there's a 0 for the polynomial, there's a 0 crossing with the x-axis. The plot crosses the x-axis at 2 points, and that tells us this is the place where there are zeros. You can go ahead and quickly check 3x cubed minus 12x squared plus 1, where does its zeros lie, and confirm that they agree with this plot, which suggests that the zeros are at, there are 2 zeros, and those 2 zeros are at x equal to 0 and x equal to 4. We can go ahead and change the range, and we can maybe make it minus 15 to 15 to see what is the asymptotic behavior of the function. That is, when x goes large, how does the function behave? And in this zoomed out plot, we're looking the plot from far away. We see that the function diverges at negative x and diverges at positive x. So as x goes to minus infinity, the function goes to minus infinity. As x goes to plus infinity, the function goes to plus infinity. And there's some detailed behavior going on in this region, which we can, of course, look more closely by zooming into that region. And from here, minus 5 to 5 will give you the more details. The range minus 5 to 5 will give you the more details, which is what we just saw. All right, let's go ahead and make our life slightly more complicated. This time, plot a quadratic function. We'll plot a bunch of quadratic functions. The functions I'm interested in here is 2x square plus x minus 4 and 5x square plus x minus 4. These are just some examples. You can go ahead and try your own examples. You can pause this video at any time and simultaneously work on the things that you're learning. It's a really good idea to keep working together. As I explain you things here and you want to try something out, go ahead, pause me and do your thing. So let's go ahead and plot this, and see I've mentioned plot legends as expressions so that I can actually identify which plot corresponds to which function. So I get this quadratic function in orange and another one in blue. The difference between the orange and the blue, if you notice carefully, is that orange is more curved up. It has, both of them have bowl shaped, both of them are bowl shaped facing up, but orange one has a higher curvature than the blue curve. This is something that even if we did not know by looking at these functions, we could plot it and quickly see it. The curvature of a quadratic function is always related to its coefficient of x square. Since the coefficient of x square is larger for the orange curve than the blue curve, the curvature is also bigger for the orange curve, and that is something we can see here visually. It's very, very important to understand or even predict what is going to be the function's behavior before we plot it. Usually we are not accustomed to thinking like that, and we blindly use a computer to plot it, but it's a good exercise to anticipate what the function is going to look like when you plot it, and then when you plot it you should examine what does it look like. Is it agreeing with your expectations? Is it what it is that you expected to see, or it's something different? If it is something different, you can zoom in, zoom out, and play around with the range of the plotting, with other functions, other options in the plotting, and you can understand the function better. Okay, let's go ahead and do some more plotting. In this example over here, I want to plot these three functions. So these 2x square minus 4x plus 1, 2x square minus x plus 1, 2x square plus 4x minus 5 in the range x minus from minus 5 to 5. Go ahead and execute it. These are the three functions. These are the three plots that I get. Now it's hard for me to say which one is orange, which one is green. So let me go ahead and add the option. Now the options, plot legends, all the options are always added after the main arguments of the function have been done. So plot function as minimum requirement is 2 arguments. This is the first argument. The second argument is the range of x. After that I can add as many options as I like. And in order to see the options, I will say plot legends and I will click here expressions, and that's it. So here are my three functions. Why are these three functions different? Green function has a minima over here, the orange one has a minima over here, the blue one has a minima somewhere over there. The minimas are different, their curvatures appear to be same, and the minimas are located at different value, and their minimum value is also different. So why is that happening? We want to understand that. So in order to understand that, let's go ahead and plot the most simple quadratic function, which is x square. And x square simply looks like a bowl-shaped curve. So what we notice by comparing this shape and that shape is that essentially a quadratic function is a bowl-shaped curve. It can curve upwards or downwards depending on the coefficient of x square is positive or negative. If I do minus x square, I get that. Now all these other variations of quadratic function, what they are doing, they're just shifting the zeros. Or if the coefficient of x square is different, they will make the curve more or curve less. Apart from that, the basic behavior of quadratic functions is all the same. The reason we are discussing quadratic functions here is because quadratic functions are something which are extremely important in physics. They show up everywhere. One of the reasons of quadratic functions appearing in many places is because anytime you combine two functions to form a minima, that minima can be approximated by a quadratic function. All right, let's go ahead and understand this further by understanding quadratic function. So what we'll do in this particular exercise is we will take the quadratic function ax square plus bx plus c, which is the most common quadratic function. 0 is not required. 0 will say that find the roots, but we just want to plot the left hand side of this equation, that is ax squared plus bx plus c, and I want to see what happens when I change a, b and c. This is how I can understand what is these different parameters do for the function. In order to do that, I'll use manipulate command. And remember, last time we discussed this at great length, how to use manipulate command. So this is an example where we'll use manipulate command to understand how does these three parameters varying a, b, c works. So let's go ahead and actually build it up slowly. So this is the function. If I execute it, the outcome will be a plot with three sliders for a, b, c. As I change a, as I change b, my plot will change. But in order to learn, let's construct this whole thing step by step, and this is a good way of this is a good exercise in thinking how to actually do to construct complicated functions. At first look, when you look at this piece of code, you may be scared that what's going on over here, but we'll break it down for you in simple terms, and we'll build this complicated looking expression step by step. So let's go ahead and do that. I want to first plot. I want to simply first plot x squared in the range -5 to 5. Let me get that first. Once I have control of this, I will say I want to make it more complicated. Maybe I want to add x and see what happens. Great, now that we've got this under control, what we'll do now is so this is my fundamental function that I want to use. I will wrap this into the manipulate layer. I'll take a manipulate function and wrap this thing inside that. So I'll go ahead and in the beginning, I'll say manipulate. So there's manipulate. The auto completion allows you to complete some of these things very quickly. Now for manipulate, I want to say, what do I want to manipulate? I need a parameter. I have not put any parameter over here, so let me add a parameter. Let me say the parameter here is a. Give a space, so a is different from x squared. This is a times x squared, and over here in the round brackets, I say that a is a parameter for manipulate. So I say a, and I say a goes from, let's say, -5 to 5. Okay, let's not, so that we're not confused, let's make it -10 to 10. Okay, x is -5 to 5 and a is -10 to 10. Let's go with that. Now I'll execute this. So what does this do? So it says that manipulate the plot function for a between -10 and 10. And what's going to do is it's going to pick some initial value of a so that it can actually make some plot. It can execute the plot command for some value of a. Otherwise, if a is not defined, plot command won't work. So this will automatically pick a value of a, and in this case it will just pick the first initial value of a, that is -10. So as a consequence, you get an inverted parabola, an inverted bowl, because a it has chosen as -10. If I click on this plus, it expands it out over here, and I see that there is a -10. A is set to -10. I can move the slider and change the value of a, and as I slide and change the value of a, you see that pretty much nothing is going on, and then suddenly at around over here, when a was small, close to 0, the shape flips. But when it appeared nothing was going on, what was actually happening was the scale on the y-axis is changing. The scale on the y-axis is changing. As I smooth the slider, the scale changes. Notice that again. I'll move the slider. As I move the slider, the scale changes, and the curve appears to be the same. This curve appears to be non-changing, and that is because scales are adjusting. So I need to fix these scales so that I can see actually the function is changing. So let's go ahead and do that by adding an option to plot function. Notice that I'm adding an option to the plot function. This is the square bracket that is closing over here. So this, everything inside this square bracket and this square bracket is the arguments for the plot function. The option I want to use here is plot range. Now you might start to feel that where do you find all these options? All these options are available in the manual of Mathematica, that is in the help section of Mathematica. All you have to do is just select this and then click F1 on your computer, and you'll be able to see the information about the plot range. If you want to find the options for a function, you select the function and press F1 on your computer. It'll open the help for that function, and in that function's description you can go and find what are the options available to do various kinds of manipulation. So let me give you a quick introduction to that. If I press F1 on my computer, this will open a help. It shows plot over here, and then I can go into details and options, and I can go through this. This is extremely detailed, and there are lots of information here, and these are the options. So it says plot has same options as graphics with some additional with following additions and changes. So it gives a list of various options available for plot. But this is not a really good way of learning. You should learn by examples. So examples are given over here, so you can go through basic examples, or you can go through the scope, which gives what are the other ways of using the function. And probably the most useful at this point might be options, so that you can see examples of various options and see how to control. So for example, plot range, here is the detail of option, how I can control the plot range. Okay, so let's go back to our work, and here I want to introduce plot range, and I will say I want y-axis, I want x-axis to be between -5 and 5. So let me specify that -5 to 5, and then I want y-axis to in the range of -10 to 10. So this will freeze the frame for me. Great. So here we go. The frame is frozen. Now you see, as I change A, the curvature changes, and at some point curvature becomes very small, and then suddenly it flips over very close to x equal to a equal to 0, and very close to a equal to 0 it flips over, and there we go. As I increase a, curvature of the bowl of the parabola becomes higher and higher. Okay, great. So now that we have accomplished this much, we'll go ahead and add more parameters to this. I'll add a parameter b over here and a parameter c over here, and I'll go ahead and specify all those parameters with comma separated arguments. I'll say b is also -10 to 10, and c is also -10 to 10. I'll execute that, and you see when I do that, I get a little parabola over here. Fortunately, it didn't go out of the range. I mean, these choice of parameters could have been such that my plot may have ended outside the frame. For example, if I make this c as -50, I will see no plot because my parabola is way down. I don't see it. So don't get surprised if something funny happens with your choice of parameters. Go back, think about it, and fix it. All right, so I've got these 3 parameters here. I'll go ahead and expand them by clicking on these little pluses and minuses, and I'll go ahead and first increase c. Let me pick it up, bring it up into the center over here. Now I will change b, see what b does. B does something interesting, isn't it? All right, a, you know what it does. A changes the curvature, and at some point it'll change the curvature from negative to positive. Okay, great. Now that we know what a does, let's just leave a over there. Figure out what c does. What does c do? It's a very simple thing. C simply lifts the entire parabola up and down. It just adds a constant value to the whole function. So all it does, it lifts the entire parabola up, or it brings it down. Now b does something interesting. B changes the position of the minima. It changes the zeros. Well, of course, c also does that. By moving the whole entire function up and down, the zeros change. The zeros are the crossing of the parabola, with the x-axis, this and that. As I change C, zeros change. As I change B, also zeros change, but you see just moving up and down. The minima is not moving simply up and down, it's also making some sort of curve. Can you find out what is that curve? So I leave that as a homework exercise for you to figure out how is the minima changing when I move B. You see, do you have a guess? You should make an educated guess and then go back and test your theory whether you can find out how the minima changes or moves around as you change B. That is, what is the trajectory of the minima of a parabola when you change the parameter B. Can you work out its equation, plot it on the same graph, and then move B around and see that minima is actually moving on that? Okay, I'll leave this as a homework exercise for you, and we'll talk about its solution at a later time. Great, so let me just quickly recap. What did we learn here? Changing A changes the curvature, changing B shifts the minima left and right, up and down as well, and changes the zeros. Changing C only leaves the minima up and down and changes the zeros.